after the discussions of a series of lectures on quantum mechanics, I have already started giving lectures on thermodynamics of electrochemical cells. And lecture 5 today I shall discuss the type 1 electrodes. All of us already aware of the fact that a cell is consisting of the two electrodes. One is anode, where the oxidation occurs and the electrons are generated, and other is cathode, where the reduction occurs and the electrons are consumed. These electrodes are of mainly three types: type 1, type 2 and type 3. I shall try to explain every details of the type of electrodes: electrode representation, electrode reaction, electrode potential, and any applications of this electrode. If available, then we shall discuss every aspect of these electrodes. Today, I shall try to explain the type 1 electrode. It is a very important type of electrodes, and this type 1. Type 1 electrodes I can define as element in contact with the ion of the element in solution. The element remains in contact with the ions or of its ions, so which is in solution. So this electrodes, this type of electrode having the different forms, and the one form I can write here, the metal one, metal ion electrodes, and its representation say N plus, and it is in solution, and oblique N solid. N is the valency of this metal ion. And the electrode reaction, which I shall represent this electrode as if it is placed in the right hand side of this cell where the reduction occurs. And naturally the reactions will be also the reactions and the potential so developed, I call the reduction potential. And this one, electrode reaction N plus Ne, and giving this N solid, and it is in solution. And this is the reduction. This process, electrode process, is the reduction process, and so potential of this electrode, obviously it is the reduction potential, and reduction potential I can write E, and N plus oblique N, and equal to E naught of N plus oblique M. This is the standard electrode potential, and minus RT by NF, and L, activity of a metal solid divided by activity of metal N plus solutions. And we know the activity of this pure metal in solid equal to 1. So this one we can write E naught m n plus oblique m, and this is equal to 1, and if we write in numerator, then it will be plus RT divided by mf and ln activity of m plus solution. So this is the expressions of this electrode potential of this metal arm. So this electrode, this one is known from the table of a textbook. Examples, I can cite some examples as zinc ion in solution, oblique zinc solid, and cadmium ion in solution, oblique cadmium solid, silver ion in solution, oblique silver. And if we choose any one, this one, then it will be cadmium 2 plus in solution, and plus 2 electrons, 2 gram equivalent of this reaction occurs, and it is the cadmium solid. And this potential, say cadmium 2 plus oblique cadmium equal to E naught of the cadmium 2 plus oblique cadmium and plus RE by 2F and ln activity of a cadmium 2 plus. And at 25 degrees centigrade, and its value is minus 0.40 volt and plus 0.059 by 2, and it will be log of activity of cadmium 2 plus. So this electrode is having several utility. As for example, you know this cadmium is a very poisonous metal, and it is actually found in river water, in the minings, from this mountain, and this cadmium may cause the softening of the bones and the kidney failure, etc. And the amount of cadmium concentration in river water, I can easily estimate by the use of this potential of this electrode. And for example, if you say here is a cadmium electrode, this is negative electrode, and here this river water which contains this cadmium 2 plus, and here one secondary reference electrode, and it can be taken as a saturated calomel electrode whose potential is known to us. So this E cell equal to E of this saturated calomel minus E cadmium 2 plus that cadmium, and this value is 0.2415 minus, and instead of this one I can write here minus 0.40 and plus 0.059 by 2 and log activity of a cadmium 2 plus. So this one is determined by means of potentiometer, and from this value we can easily get this activity of cadmium ion in this river water, and such a solution is very cadmium solution in mineral water is very dilute, and so this one activity of a cadmium 2 plus can be replaced by the concentrations of cadmium 2 plus, and this is so sensitive. This experiment is so sensitive that the micromolar 10 to the power minus 6 molar concentrations of cadmium could be easily determined by this experiment if we use very sensitive galvanometer. This electrode is having also some sort of disadvantages. The more reactive metals like sodium, potassium, calcium could not be used in aqueous solutions. Not only that, if the zinc electrode could not be used in acid solutions, as zinc reacts with the acids and producing this hydrogen. So instead of this, when this electrode fails, we can use the type form of these two electrodes. This is called amalgam electrode. In this case, amalgam electrodes, in this case the metal is dissolved in mercury, and the activity of this metal is moderated or diluted. So it will be more safe to use in aqueous solutions or some other solutions of where this pure metal arms are phase. So naturally this amalgam electrode, the metals more reactive than mercury could be used in this case. So example, I can represent this type of metal, this type of electrode representation. This metal N plus, and it is in solutions and oblique, and here this M in dissolved in mercury, and here platinum, this connecting inert metal is used. In this case the reaction is Mn plus Ne and giving, and this is in solutions, plus Ne and giving this N and in mercury. And the potential of this electrode, reduction potential, of course, it is the Mn plus oblique M in mercury, and this one equal to E naught Mn plus oblique M and minus 0.0 minus RT by NF, and it is Ln, activity of this metal in mercury, and divided by activity of this metal in solutions. This one, activity of this one is not equal to 1, it is always less than 1. It depends on the concentrations of this metal in amalgam. Let us take an example. The cadmium 2 plus solutions and oblique the cadmium in amalgam. This is one example. Or zinc in solutions and zinc metal in amalgam. These are the examples. Or you can say silver plus solutions, and here the silver in amalgam. These are few examples. So this potential of this electrode, if we write this E, if we write this reaction, cadmium 2 plus in solutions plus 2E and giving this cadmium in amalgam. And the potential is, say suppose amalgam electrode potential equal to activity standard value N into N plus 2 plus cadmium, and this one minus RT by Na, RT by here 2A into Ln activity of this cadmium in amalgam. This can be taken in a bracket and plus RT by Na, RT by Na into Ln activity of this Am in plus solutions. If we keep this concentration of this cadmium in amalgam fixed, then this is also fixed at a given temperature. So all the term within the bracket is fixed, and let it be the E amalgam naught plus RT divided by Na and Ln activity of cadmium 2 plus solutions. So it will be the activity of this cadmium 2 plus and solutions. If we like to determine this value, then actually we have to construct a cell. Cell is cadmium, and here say cadmium sulfate solutions and oblique, and the cadmium in mercury. This pure cadmium is more reactive than this one, so this one will be kept in this left hand side. This is negative electrode and this is the positive electrode, and this E cell, which could be determined by means of potentiometer, this one will be E right hand side electrode minus E left hand side electrode, and this will be right hand side, this one E naught amalgam and plus RT by Na, RT by here this twice A, and this Ln activity of cadmium 2 plus solutions, and in this right hand side and left hand side we can write this E naught and cadmium 2 plus cadmium and plus 0 point RT by NF into Ln activity of a cadmium 2 plus solutions. So this one and this one will cancel, and giving this value E naught amalgam and minus E naught activity of E naught cadmium 2 plus oblique cadmium. This is obtained from this table, this one obtained from this potentiometer, so this could be determined. And from the knowledge of this one, we can also calculate the activity or concentrations of the cadmium in amalgam. Now the third type of electrodes. Now, third form of the first type of electrodes, third form, and this is the very popular, and it is the gas electrode. Gas electrodes. And in this case, this gas is the gas is bubbled. The gas is bubbled around an inert metal dipped in a solution containing the arm of this gas. And very popular of this type of this electrode is the hydrogen electrode. Hydrogen electrode. This hydrogen electrode could be represented as this H plus, and here it is in solutions, and oblique here hydrogen gas and passed at the atmosphere. So this simple, very simple electrode. Here the platinum electrode, and platinum electrode. Here this hydrogen gas is passed at a P atmosphere, and here the acid solution which contains this hydrogen ion in this acid solution. This is the platinum coated with platinum black, so that it will give more surface area. And this catalyst accelerates the electrode process. The reaction is H plus, and it is in solution plus electron and giving this half of hydrogen, a gas, and P atmosphere. So the catalyst actually, this platinum catalyst actually catalyzes this sort of electrode process. First, this hydrogen gas adsorbed on the platinum surface, and it is the hydrogen adsorbed on this platinum surface. And the heat of adsorption supplies the amount of heat which will dissociate this hydrogen molecule, and giving this 2H plus in the platinum, two hydrogen atom in platinum, and this one again gives this 2 hydrogen ion plus 2 electron, and 2 electron remains on the surface of this platinum. And so this process, the mechanism by which the platinum accelerates this process, and the potential of this electrode is E hydrogen ion oblique hydrogen gas equal to E naught hydrogen ion in solution, and hydrogen gas minus RT by NF and Ln. Activity of hydrogen gas root over, and activity of hydrogen ion in solutions. This one is equal to 0 by convention. So this electrode potential of this, so the potential of this hydrogen electrode is equal to minus at 25 degrees centigrade 0.059 by 1, and it is the log. And this one, this root over of activity of hydrogen gas is actually the pressure of this hydrogen gas in atmosphere unit, and if usually this P hydrogen has been taken at 1 atmosphere, so this one equal to 1. In this case, 1 by activity of hydrogen ion and solutions. And this is called the pH. So this electrode minus 0.059 and pH of this solution. So where this platinum electrode is deep and hydrogen gas at 1 atmosphere is passed through these solutions. So this potential, if we determine this potential by coupling with a secondary standard electrode, it is possible to determine the pH of the solutions. This electrode is very good, but here also there is some limitations. These unsaturated hydrocarbons should not be there in the solutions. Oxidation reduction, oxidizing reduction reducing agents should be absent from the solutions. Not only that, heavy metals is to be absent in the solutions, otherwise the hydrogen gas will react with this heavy metal and precipitate the heavy metals also. So this electrode is very much useful, though its setup in laboratory is to some extent difficult. So all about this gas electrode and several other gas electrodes are also there. Say chlorine electrode, chlorine electrode in this case representation will be like that, Cl minus solutions and oblique Cl2 gas, Cl2 gas and P atmosphere. And the reaction is that half Cl2 plus Cl2 gas and plus electron and giving this Cl minus solutions. And the bromine electrodes, we can also say this reaction Br minus and it is solution and Br2 and it is liquid and platinum electrode. And it could be shown as here the bromine liquid, here say potassium bromide solutions, and here some platinum electrode and this is the terminals of this electrode. And the iodine and fourth one and the very popular the oxygen electrodes. It is also represented as OH minus solutions and oblique this oxygen gas at 1 atmosphere normally. So the reaction is the half oxygen gas plus water plus twice E and giving this twice OH minus. So this electrode also depends on the hydroxyl constitutions of the solutions, but this electrode is rarely used that as this equilibrium is not attained very quickly. And the next one, the non-gas, fourth one, non-gas, non-metal electrode. And this bromine, one example is bromine minus solutions, and this one, and Br2 liquid and platinum, and other is I minus solutions, and here I2 and solid, here also platinum as iodine is non-conducting. So these are all about the type 1 electrodes, and in my next lecture I shall explain the type 2 electrode, which is more important than this one. Thanks to you all who are watching this video. If you like